Absolute value means that you're going to have a positive function, so that means that you can have negative and positive x values, but your y value will always be positive. So if we were to graph the absolute value function of x, let's make a table of values. So we have x and y. Let's go -3, -2, -1, 0, 1, 2, 3. If we plug x into this equation, the absolute value of -3 is +3. The absolute value of -2 is +2, and so on and so forth. So all of our y values will be positive. So if we graph this, if we go 0 and 0, 1 and 1, 2 and 2, 3 and 3, -1 and +1, -2 and +2, -3 and +3, our graph will look like this. So it makes a V. And as you can see, nothing is in the lower two quadrants. Everything is in the top two. If we were to describe the domain of this function, the domain would be x is an element of all the real numbers. The range would be y has to be greater than or equal to 0, because it has to be positive. If we were to say this was line 1 and this was line 2, well, the slope of line 1, let's go slope, would be you go up 1 over 1, so 1 over 1. The slope of line 2, you go down 1 over 1, so -1 over 1. So as you can see, this one is positive and this one is negative, so they have the opposite sign. So one of the lines is positive, one of the lines is negative. If you notice, right here, straight down the middle, where the graph touches the x-axis, it's symmetrical. So this is over 2, this is over 2, this is over 4, this is over 4. So this is our axis of symmetry. So the graph is symmetrical about this point right here, which is our x-axis, our x-intercept, and this is called our critical point. So the critical point is where the point on the graph changes directions. So our critical point is our x-intercept. For this one, we are going to graph the function of the absolute value of 3x plus 6. So what we're going to do is we're going to graph it normally. So our y-intercept is our b value, so it equals 6. So 1, 2, 3, 4, 5, 6. And our slope is equal to 3 over 1. Or you could write this as -3 over -1. So if we were to draw this line, we'd go down 3 over 1. Oops. Down 3 over 1. Down 3 over 1. When you connect the lines, anything that is in the positive part of the graph, do a solid line, and everything below the x-axis, draw as a dotted line, because this is going to change. So our critical point is where it touches the x-axis, which is at -2. So this is our critical point. So that means it's symmetrical about this point. So we know that we can graph the other end of the function this way. Please draw it straighter than mine is. So this is a drawing of our absolute value. If the slope here is up 3 over 1, so slope of 3, the slope of this side will be -3, so it's the opposite sign. With a parabola, first you're going to find your vertex. So the vertex is your P and your Q, so -2 and 2. So graph your vertex. So -2 and 2 is right here. Now your stretch will be by a factor of 2, and it opens down. So that means we're going to go over 1, down 2, over 1, down 2. So this is our parabola. Anywhere that is positive, draw with a solid line. Anywhere that is negative, draw with a dotted line. Now to graph the absolute value of this, wherever the critical points are, so our critical points, I'll put CP, they're at -3 and 0 and -1 and 0, right here, where the x-intercepts are. Those are the parts that reflect the graph in the opposite direction. So if we're going down in our normal function, in our absolute value function, we go up. So it'll look like this as your final absolute value. It should make it a W. For this one, our vertex is at -1 and -2. So this time it's below the x-axis. Our stretch is by a factor of 2, and it opens up. So we're going to go over 1, up 2, over 1, up 2. Anything that is below the x-axis draws a dotted line. And then everything above the x-axis is a solid line. From here, we need to invert this middle section. So our critical points are at 0 and 0, and 0 and -2. Those are the points in which it reflects, so it goes the other way. And we want to find the absolute value of our vertex. So we know that our x value is going to stay the same, but the vertex will be at the absolute value of your y coordinate. So it'll be at -1 and 2, which is right here. Connect your points. So this is your graph of your absolute value function. The domain would be x is an element to the real numbers, and the range would be x is greater than or equal to 0. And by x, I mean y. For the next one, our vertex is at 0 and -1. So right here, we have a stretch by a factor of 3, and it opens down. So we're going to go over 1, down 3, over 1, down 3. Now this time, everything about this parabola is below the x-axis. So when you have this, you want to find the absolute value of the vertex. So 0 and the absolute value of -1, which is 0 and +1. And the entire parabola is going to reflect about the x-axis. So it's going to look like this. So over 1, up 3, over 1, up 3. So that is the absolute graph of this. Our domain would be x is an element to the real numbers, and the range would be y has to be greater than or equal to 1, our y value in the vertex. Piecewise notation is writing it into two separate pieces to show different conditions within the domain. So if we have the absolute value function of this line, the first thing that we're going to do is we're going to set it up into the positives and the negatives. So when it's positive, 2x minus 1 will be greater than or equal to 0. And we want to do the equal sign with our positive to include the critical points or the x-intercepts. Our negative will be when it's less than 0. So we're going to solve these inequalities. So 2x is greater than or equal to 1 divided by 2. So x has to be greater than or equal to 1/2. And 2x is less than 1 divided by 2. X is less than 1/2. Remember, when you divide by a negative, you have to flip the signs. This one we don't have to, but if you did divide by a negative, flip the signs. So these are our conditions. So this is when it becomes positive, and this is when it is negative. So we're going to write y equals big squiggly brackets. Then we're going to write the positive of the function, so 2x minus 1, and the negative of the function, so negative bracket 2x minus 1. So this is for all the positive values, and this is for all the negative values. And we know it's positive if x is greater than or equal to 1/2. And we know it's negative if x is less than 1/2. So what that means is if we have the function, and it looks like this, if it's greater than 1/2, it has positive numbers. If it's less than 1/2, it has these. So that means that we'd have to flip the original function to make all the values positive. So this is the flip side of the equation. This one stays normal. And in the textbook, they'll distribute this negative in to make it negative 2x plus 1. So this is your final answer for piecewise notation for linear functions. For a quadratic, first we have to find our critical points. So I'm going to change this to x squared plus 4x plus 3 just to factor it. So two numbers that add up to 4 and multiply to get 3 are 3 and 1. So x plus 3, x minus 1. And there's a negative 1 on the outside. So that means that we have x equals negative 3 or x equals positive 1. Now we're going to do a quick sketch of our parabola. So we have critical points at negative 3 and negative 1. We know that it opens down. So it looks something like this. And with the absolute value, it would go up. When we do our piecewise notation, there's going to be two sections. Either it's going to be positive or negative. So if we want negative x squared minus 4x minus 3 to be greater than 0, this is just like the linear inequality unit. So it is either going to be between our two critical points or on the outside of our critical points. So if you look at the original function, it's positive between the 2 points. So this is true when negative 3 is less than x, which is less than negative 1. When the function is negative, these should have greater than or equal signs. It'll be either less than 3 or negative 3, greater than negative 1. So to write it as piecewise notation, you would write y, oops, I wanted to do that in red. Y is equal to big squiggly brackets, negative x squared minus 4x minus 3 if negative 3 is less than or equal to x, which is less than or equal to negative 1. And we'll distribute this negative in. So x squared plus 4x plus 3 if x is less than negative 3 or x is greater than 1. So this is your piecewise notation.